Humans have always been drawn to the unknown. The desire to learn new things has propelled humanity to where we are now. And the next logical step in our species' evolution is to venture beyond our atmosphere, to explore space, and to establish as many other homes on a grand scale as possible. However, it is much easier said than done. You see, our universe is an enormous place. We mere humans could never fully comprehend the extent of our galaxy. In fact, we have no idea what the scale of our own solar system is, let alone our universe. To give you some context, the fastest man-made object, the Voyager 1, has yet to leave the solar system. The Oort cloud, which is a theoretical collection of comets and space debris, sits at the very edge of our solar system, and Voyager 1 has yet to reach it. Scientists estimate it will take another 300 years before it gets there. If that wasn't a big enough number, there's a bigger one. You see, the Oort cloud itself has a thickness of over 2 light years, which is about 19 trillion kilometers. And it would take at least another 35,000 years for Voyager 1 to actually exit the Oort cloud, and thus, to exit our solar system. Let that sink in for a moment. 35,000 years just to leave our own solar system. Yet, on a universal scale, our galaxy is no different from the microscopic speck on your table. As time passes, our future generations may be able to achieve previously unimaginable speeds, but for the time being, let's stick to the present. Our brains are incapable of comprehending such large distances, and the numbers involved are so massive that their existence is purely rational and devoid of any more meaning. However, there is something much more extreme. Something so extreme that no words or numbers can accurately describe its scale. Infinity. Infinity is that which is boundless or endless, or something greater than any real or unnatural number. To us, infinity is nothing more than a symbol, used to describe something that has no boundaries, and thus cannot be represented or visualized. It is something beyond our dimension, something which we could never comprehend. Or could we? Is it possible to see the infinite within finite terms? Is it possible to bind the unbindable? Perhaps these were the questions a Dutch artist named M.C Escher wanted us to ponder when we saw his work, to question the principles of thought that went into the creation of his artwork. The artwork that logically defined the limitless within the confines of a boundary, and the artwork that captured infinity. Maurits Cornelis Escher was a Dutch graphic artist who created woodcuts, lithographs, and mezzotints inspired by mathematics. Escher was incredibly intelligent, with an exceptional talent to understand patterns and use geometry effectively. He gained popularity in the late 20th century, and in the 21st century, he has been honored in exhibitions all over the world. M.C. Escher was a fascinating figure, because while he did create artworks that conveyed or had deep mathematical meaning, He was never the type of person who could truly comprehend the theoretical aspects of math involved in his work. His approach to mathematics was purely intuitive and visual. Escher was never an outstanding student, and his formal mathematical knowledge was limited to what he received in secondary school. He primarily created portraits, landscapes, and architectural images, as well as commercial designs for items such as postage stamps and wrapping paper, all of which he executed with increasing technical skill. But somewhere around the midpoint of his career, he underwent a transformation that shifted his focus to ideas that were completely unique, but were quite unrelated to graphic art. He writes, "I discovered that technical mastery was no longer my sole aim, for I was seized by another desire, the existence of which I had never suspected. Ideas took hold of me quite unrelated to graphic art, notions which so fascinated me that I felt driven to communicate them to others." Following this transformation, he began producing the pieces which he is now known for: the illusions, the impossible figures, and the most intriguing of them all, the regular divisions of the plane, also known as tessellations. He had successfully implemented these ideas when he was struck by yet another brilliant but difficult idea: dividing the Euclidean plane into potentially infinite populations of fish, reptiles, or birds. He desired to capture infinity within the confines of logic. This idea of capturing the indefinite will later be known as the circle limit series. The circle limit series is supported by a one-of-a-kind framework: a disk, a specific type of disk. The circle limit series consists a total of 4 pieces, each one with its own distinct motif. Each one conveys a different meaning and a certain time period in Escher's quest to capture the impossible. However, they all share the same features, like how the patterns continue to repeat until the disk is completely filled, or how the objects in the center appear to be larger than those closer to the boundary, and as objects get further away, they tend to become distorted. Of course, we must not overlook the meticulous symmetry that went into creating the 4. Consider how difficult it would be to do all of this with only a ruler and a compass. Today, we could easily achieve symmetry by using the mirror feature in almost any software. But back then, it was all done by hand. Escher was not like other artists in that he desired a logical framework upon which he could execute his ideas. He could easily have created an artwork with a subjective interpretation of infinity, but he did not. He desired an objective method, one that was logically precise, and one that could be proven. As a result, something that had to have involved mathematics. But once again, we don't believe he was actively looking for mathematical proofs that would allow him to achieve his goals. Rather, we believe he was quite busy observing, quite busy finding a solution that was purely visual. While Escher was overjoyed in theory during his studies to capture infinity, he was dissatisfied with the particular feature of the tessellations in practice. He discovered that the logic of the underlying patterns would not allow for what the real materials of his workshop demanded: a finite boundary. It's time we explained what tessellations mean. A tessellation is an arrangement of shapes closely fitted together, especially of polygons in a repeated pattern without gaps or overlapping. Examples of tessellations are quite literally everywhere. Like the one in your house, your floor tiling, they repeat until the walls cut them off. Tessellations could then theoretically continue indefinitely if the area allows for such an occurrence. If you want infinite tessellations, you can have them, but you'll need an infinite surface area to fit those infinite tessellations. This was the challenge Escher faced when experimenting with his grand idea. He had a variety of tools and materials, but they were all limited in area. As a result, Escher's ability to create repeating patterns was limited. This was the first sort of major hurdle he faced. Escher still continued to experiment, but came up empty-handed. But all of that was soon about to change. In 1954, the International Committee of Mathematicians organized an unusual event. They held an exhibition featuring Escher's previous works, crediting him for his brilliant use of geometry in near-perfect symmetry. This drew the attention of a lot of mathematicians, most of which were fascinated by Escher's work in general, but particularly with the execution of his symmetry. H.S.M. Coxeter, a Canadian, was one such mathematician that took a particular liking to Escher's work. In 1957, Coxeter was drafting an article for the Royal Society of Canada about symmetry when he remembered Escher's work. So he wrote to Escher, seeking permission to produce one of his artworks. Escher quickly and happily responded, "Not only am I willing to give you full permission to publish reproductions of my regular flat fillings, but I am also proud of your interest in them." A year later, in 1958, Coxeter sent a copy of his article to Escher. While Escher was going through this article, his eyes were instantly drawn to a particular figure by Coxeter. The Poincare disk model was depicted as a diagram. We'll get to that in a minute. Escher was intrigued by this figure and quickly understood that it was his ticket to completing his own work. This figure, he concluded, could theoretically fit infinity. How he came to the conclusion that the Poincare disk model could logically fit infinity is still a mystery to us. Perhaps he had read Coxeter's description of the image, or perhaps he's just so gifted in geometry that he intuitively recognized the concept. But the initial assumption appears to be incorrect, based on a letter he wrote to his son George. In the letter, he writes, "His hocus-pocus text is of no use to me at all, but the picture can probably help me produce a division of the plane, which promises to become an entirely new variation of my series of divisions of the plane. A regular, circular division of the plane, logically bordered on all sides by the infinitesimal, is something truly beautiful." Following this letter, he encounters a few other roadblocks en route to attaining his ultimate aim. But with the help of his mathematician friend H.S.M. Coxeter and a few back-and-forth letters, he was ultimately able to grasp the underlying foundation of the Poincare disk. This new understanding would allow him to manipulate the patterns to his liking, resulting in some stunning tessellations that logically fit infinite within a boundary. These were then dubbed the circle limit series. Before we go into the arithmetics, let's take a moment to appreciate this work on a more subjective level. A more artistic approach, if you will. To us, infinity is divine. It corresponds to something beyond what we can attain, which inspires us to unravel the mystery that surrounds it. The universe we dwell in is represented by the infinite, which signifies exploration and freedom. Not so long ago, we came across an image of the singularity before the Big Bang, which looked awfully similar to the circle limit series. A tiny point in space that contained a massive amount of information. A tiny point in space that contained literally everything. Now, to understand the logic behind the circle limit series and how Escher captured infinity, we must first understand the mathematics behind the canvas itself. The canvas here is the Poincare disk model we saw earlier, the one Coxeter used in his article. As we mentioned earlier, in the Euclidean plane, you could technically have an infinite number of tessellations, if you had the luxury to afford an infinite area. Think of it like having an infinitely big house, that you would need infinite tiles to cover the infinite floor, which, quite frankly, is impossible. So we have to turn our heads in a new direction. a different type of geometry, a non-Euclidean geometry to be specific. First, let's understand what Euclidean geometry is. In layman's terms, Euclidean geometry follows a set of rules called the Euclid's 5 postulates, or axioms. They are: a straight line segment can be drawn joining any 2 points. Any straight line segment can be extended indefinitely in a straight line. Given any straight line segment, a circle can be drawn having the segment as a radius and one endpoint as the center. All right angles are congruent. And the fifth, if 2 lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than 2 right angles, then the 2 lines inevitably must intersect each other on that side, if extended far enough. This postulate is equivalent to what is known as the parallel postulate. Let us now disregard the first 4 and concentrate just on the 5th postulate, the parallel postulate. For a long time, this postulate has been a source of debate among mathematicians. Why? Because it stands out from the rest. It's not practical to follow, in the sense that we can't draw a line forever to see if they meet or not. As a result, some mathematicians theorized a new sort of geometry, using the appeal to extremes method. What we call the hyperbolic geometry is one of these new non-Euclidean geometries that disagree with Euclid's 5th postulate. Consider a hyperbolic plane to be curved like a horse saddle. If we had to extend the plane further, it would be a disaster to say the least. So a French mathematician by the name of Henri Poincaré proposed an ingenious idea. He proposed a method to represent this new hyperbolic geometry in terms of Euclidean geometry. This model is what we call the Poincaré disk model. The points of the hyperbolic space will be represented as points inside the unit disk of the Euclidean plane, according to Henri Poincaré, and the entire hyperbolic geometry will be stored in this disk. Inside the unit disk, he explained, there would be 2 straight lines, one of which would pass through the center of the circle and thereby its diameter. Secondly, the arcs of circles intersecting the disk's boundaries at right angles. Although these seem to be curved, they are straight in actual hyperbolic space. He also proved with a couple of equations that the lines within the circle would be of infinite length. The same was proven for the area of the hyperbolic geometry as well. One feature of hyperbolic space is that it can have an infinite number of tessellations. So, if we represent the entire hyperbolic geometry with infinite length within a finite disk, we could theoretically avoid the need for an infinite area. Another thing to keep in mind is that while the shapes that move away from the center appear to be shrunk, they're actually the same size compared to any other shape in the tessellation. Consider this a byproduct of attempting to fit a non-Euclidean geometry into a Euclidean plane. It is upon these principles that the circle limit series is built upon. Escher carefully analyzed the line work of the Poincaré disk and used them as a guide for his own creations. Ironically, the amount of freedom he had with the creation of the figures were limited to what the line work permitted. Now armed with the new knowledge, let's decode the circle limit series. Roughly speaking, we now have 3 infinities to work with on the Poincaré disk, and thus, also the canvas or the base of all circle limits. We'll be honest with you, we're not sure which of these infinities M.C Escher was trying to convey. However, based on the previous letter, we can deduce that he may be discussing how his motifs become infinitesimally small and infinitely close as they reach the limit. But for now, we cannot say for certain. So we'll go through all of them and piece them together with CL4, angels, and devils. The line extends to infinity, so the point nearest to the boundary of the circle is at infinity. As we saw earlier, Poincaré proved that the lines extend till infinity, and the entire hyperbolic plane is within the disk. So if we fill the disk with tessellations, then the bat or the angel at the furthest point from the center is at infinity. Hyperbolic area represented within the Poincaré disk is infinite, so we could fit an infinite number of tessellations. This one is self-explanatory. Let's also figure out the logic behind Escher's argument in his letter to his son. I am trying to glean from it a method for reducing a plane-filling motif, which goes from the center of the circle out to the edge, where the motifs will be infinitely close together. He also writes, a regular circular division of the plane, logically bordered on all sides by the infinitesimal, is something truly beautiful. Let's start with something we already know. We can tessellate any number of sides in hyperbolic space. So, as we fill the entire Poincaré disk, you can see that we are creating polygons with many sides, and as they approach the limit, they shrink. However, keep in mind that this occurs due to distortions only in the Euclidean plane, and they are all the same size in hyperbolic space. We can now say that as we move closer to the edge, the density also increases, because there are more bats or angels in any given area than, say, at the center of the disk. Because the area of the disk is infinite, we could theoretically go on indefinitely with the tessellations. If we do that, we will eventually reach a point of infinitely small polygons, or in this case, bats and angels. Because the density is so high, possibly even infinite, the motifs are infinitely close together within a given area. In other words, they are squashed together, but only in our Euclidean representation of the hyperbolic plane. They are actually infinitely far apart in hyperbolic space. The entire circle limit series is a fascinating piece of art. The complex mathematical foundation it's built upon, and the artistic approach that went into making it. To this day, we're still hesitant to believe M.C Escher actually went through the trouble of learning the different mathematical equations and formulae to make his artwork. Thomas Waiting writes, of course, the assertion of congruence applies just as well to the various motifs that compose the patterns of the circle limit series. Although there is no evidence that Escher understood this assertion, I am sure that he would have been delighted by the idea of a hyperbolic eye that would confirm his procedure for capturing infinity and would refine its meaning. Professor Thomas Waiting is one of many that hint at Escher's limited understanding when it comes to the mathematical side of his creations. Yet, he was able to delight not only the general population, but also the true hardcore mathematicians. To us, this artwork has been a journey into the unknown. Every time we thought we solved a piece of the puzzle, there was only more unknown waiting for us to explore. We still don't believe we have found the exact truth and the objective behind why Escher created this piece, or what he wanted to convey exactly. But we are sure he did want us to contemplate these questions that would lead us down a path full of mysteries. He wanted us to see the local finite and contemplate the global infinite. After all, humans are driven by mysteries. Mankind is only here today because of the unknown. We are incapable of imagining that time could ever stop. For us, even if the Earth should cease turning on its axis and revolving around the sun, even if there were no longer days and nights, summers and winters, time would continue to flow on eternally. We find it impossible to imagine that somewhere beyond the furthest stars of the night sky, there should come an end to space, a frontier beyond which is nothing more. For this reason, as long as there have been men to lie and sit and stand upon this globe, or to crawl and walk upon it, or to sail and ride and fly across it, or to fly away from it. We have held firmly to the notion of a hereafter, a purgatory, heaven, hell, rebirth, and nirvana, all of which must continue to be everlasting in time and infinite in space.